Yes. All right. Will my pen still work? Yes, it will. All right. It's going to work. That is awesome. Okay. So now I have these recorded, so if you need to go back and watch, you can. So the bird's flying due east, and it wants to know what's the instantaneous velocity at time is equal to 8 seconds, 8.00. So what do I do, guys? So we're wanting to do what? We've got to find the velocity. So notice it said instantaneous. So what's the first order derivative from displacement? Well, it's velocity. So we take the first order derivative, correct? And so what's that going to be? Well, that term is gone. And now we're left with what? 12.4 meters per second, because when you take the derivative of t, it becomes 1, right? Because you subtract 1. But this first term is gone because there's no t term on it, right? And then this one becomes what? I did write that equation correctly. Yes, that's negative, and that becomes what? 3 times 0.0450 meters per second cubed t squared, correct? So now what do? I just plug in for t, do I not? This is grocery store arithmetic. Don't you just love this stuff? This is so easy. All right. We just plug it in. Plug it in, plug it in. Don't forget your Glade commercial. That'll help you. And we have what? 8.00 seconds squared. And we should get an answer of 3.76 meters per second. Close to that. Now, guys and gals, remember, now look how the math works beautifully. All right, look, you have seconds squared. Well, that cancels out the cubed and leaves seconds. And notice now, remember when we talked about dimensional analysis? Did my answer work out to keep the dimensions correct? Do I have good dimension matchup? I sure do. Because here's meters per second and here's meters per second, and that's what we're looking for is velocity. So you check your dimensions. All right? Any questions? 3.7. Again, y'all, rounding. I know some of you might, a little bit different on rounding, but again, let's look at significant figures here. Did I write everything right? I should have. Yeah, 12. Yeah. Okay. So we've got. Let's see. How many sig figs we got here? We've got 3 there. 3. Yeah. So 3 significant figures. 3. Actually, though, we probably could have done what? Because we subtract here the lowest number to the right of the decimal. So it's still 3 significant figures. Okay. So actually, I probably should have said what? Since we're adding, I should have rounded it up to 3.8. Okay. Because one significant figure to the right of the decimal. Okay. Okay. Now remember, y'all, I'm not going to be extremely nitpicking with that. But if you look at significant figures, because we were adding or subtracting, that's what we were doing. That's what you would write, okay? All right. Any questions? That's pretty easy, isn't it? All right. Are there any others that's just driving us absolutely nuts? Anyone have one in particular? I'm trying to look here to see if I see any that might need a little extra attention. It's been a year since I've worked these, y'all, so I have them worked out on paper, but when you're not face to face or virtual to virtual, I don't keep everything in memory. Yeah, number 14, is that the one I'm thinking about? Yeah. All right, since no one's saying anything, are y'all asleep out there or something? Oh, someone did make a comment. Okay, all right, thank you for that. Okay, good. I think it's doing okay here, but thanks for that comment, okay? Because it seems to be working fine. I'll find out when we're done and I hit stop. But thanks for that. Okay? All right, let's look at, you want to look at number 14? Anybody in opposition to number 14? I'm going to erase. I guess not. Okay. Number 14. A race car starts from rest. So we want to draw it. So we got a race car. Close enough. And travels east along a straight and level track for the first 5 seconds of the car's motion. The eastward component of the car's velocity is given by this function. All right, so let's write that down. So for the first 5 seconds, so, you know, let's just say that's first 5 seconds. From here to here, let's just say that is, time is 5 seconds. I probably didn't write it right, did I? 5.0 seconds. Okay, so 5.0 seconds. There we go. And what does it say? All right, so its velocity is given by this. Velocity in the x direction, velocity in the x direction with respect to time is equal to 0.860 meters per second cubed t squared. Right? Calculate the average acceleration for the time interval from t is equal to 0 to t is equal to 5 seconds. So all right, so A says to do what? We want to know acceleration average for time interval t equal to 0 to t equal to, oh, darn it. I'm looking down at the next part of the problem. I know some of y'all thinking, where the heck is he getting at? I do that all the time. I hate it when I do that. Sorry. All right, what is the acceleration of the car when the final velocity is 12 meters per second? Sorry about that. So what is the acceleration of the car when, I need to just keep my hand on the book. The velocity in the x direction is 12 meters per second. 12.0 meters per second. Okay, guys, now what is that? What is that right there? Do you notice how that's written? Now, I wrote it just like the book wrote it, but if I was writing this problem, I wouldn't write it exactly like that. Remember, I told you this today. There's 3 different forms of variables. They all mean the same thing. That is final velocity. You could actually write it this way. The final velocity in the x direction, and I probably should have put x first, but anyway, is what? 12.0 meters per second. So that is the final velocity. Okay, so how in the world do we find this? Now notice, let's go back and look at it. Notice it says that for the first 5 seconds, the car's motion is eastward, and it is given, and the car's velocity is given by this function or this equation. All right? What is the acceleration of the car when its final velocity is 12 meters per second? Now, I know it doesn't tell you anything about acceleration, but let me just throw you a hint here. Let me just show you something. If I were to take the first order derivative from velocity, what are we going to get? Will I have any t component left? Yes, I will. So if I take the first order derivative of that function, that equation right there, we'll have t, won't we? We'll still have t left. So what does that tell me? That tells me that the car is doing what? Is it accelerating? Yes, it is. And is it constant acceleration? No, it's not. And you say, well, now, Mr. Shields, how do you know? Because there's still t left. If you take the first order derivative of that right there, you'll get acceleration. And it'll be acceleration with respect to t is equal to 2 times that value, t. When you take a derivative and there's t left, and you take the derivative of velocity, the first order, or the second order of displacement, and you still have t left in your equation, That should sound a bell that acceleration is not constant. It's not constant. Okay? So that's how we know it's not constant acceleration. Now I'm kind of working this backwards, but I'm just going ahead and letting you know that it is accelerating. It has to be, y'all. It has to be. And two, that the acceleration is not constant. But that's not helping us find the acceleration, is it? Well, we're getting there. So what is the acceleration of the car when notice this is final velocity. Final velocity. Well, guys, what are we missing? Aren't we missing something here? We're missing something, aren't we? We sure are. We're missing what? We're missing time, aren't we? Yeah, I know some of you are just jumping up and down about taking that derivative. Well, guys, we don't have time. See, look, how do I find time? Because look, there's time right there. Well, Miss Shields, we were given 5 seconds. Yeah, I understand that. But that was the first 5 seconds. And again, that's almost trick, but it's really not. But I know it seems tricky, but it's not. So we don't know the time, do we? We know the final velocity. We know the function of the velocity. But we don't know the time interval because this is for the first 5 seconds. But when we read the final velocity, we want to know what the acceleration is. We got to find the time first. Well, how in the world am I going to do that? Well, look, guys, you're given an equation. You're given a final velocity because, y'all, that's final velocity. So could we not work it like this? Oh, excuse me. I'm getting ahead of myself. Let me make sure I'm doing this right. Yes, I am. Okay. That's 0 meters per second cubed, t squared. All right, y'all, solve for t. Solve for t. So we wind up with what? We wind up with t is equal to 12 square root of. And we get an answer of 3.73 seconds. Now notice, you say, now is that within the limits of my problem? Well, yeah, because the function was good for what? 5 seconds. So we're within our limit there. Does that make sense? You see what I'm saying? We're within the first 5 seconds, so this function is good for the first 5 seconds. All right? Now we have a time. Right? Now, some of you that are real itchy about doing a derivative, now we can do the derivative, can't we? We sure can. Now I'm going to erase. I hope you have it all written down. So we come in here now, and we say that let me just rewrite this, and this was x with respect to time is 0.0860 meters per second cubed, and that was t cubed, right? Or t squared. T squared. So take the first order derivative, so acceleration in the x direction with respect to time is equal to 2 times 0.0860 meters per second cubed t. Now plug in your time, and we're going to say 3.73 seconds. So 2 times this times 3.73 seconds. And we get an acceleration in the x direction of 6.4 meters per second squared. Okay? Okay. Any questions? So I know that you think, well, how in the world do you know how to do that? Well, you've got to look at what you're given and look at what you got to find. You did not have time. Well, you did have time, but you had it for the first 5 seconds. But we did not know, all we knew was the final velocity. The function, the final velocity for the first 5 seconds, and it started from rest, we knew that. So you can find the time when you're given a function and when you're given the final velocity, okay, or the equation. That's a good one. I like problems like that because that really makes you think. But there's your final answer. That's a good test question right there. All right. All right, any others you'd like for me to look at real quick? Anyone have some that are driving you crazy? Now, some of these are kind of lengthy. What about number 30? Number 30. Okay, we have a small block that has a constant acceleration as it slides down a frictionless incline. All right, so how do I want to draw this? I always like to draw my inclines like this. And we got a small block, and it's going that way. And this is frictionless. You always draw it and label it. And it says it has what? Constant acceleration? Yeah, so we need to write that down. Constant acceleration. I'm going to abbreviate acceleration. Hope that's okay. So it's frictionless, it's constant acceleration. As it slides down a frictionless incline, the block is released from rest. So that means what? When it's released from rest, its initial velocity has to be 0, right? So you need to write that down. Initial velocity is 0 meters per second. And its speed after it has traveled 6.8 meters. So let's say from here to here, let's just say from here to here, this is 6.8 meters. Okay. And by the way, that could be written as what? Change in x is 6.8 meters. How'd you know to write change as x? Well, because it started from rest, and then after it traveled, its speed after it traveled 6 meters to the bottom of the incline is what? 3.8 meters per second. So that's what? Well, this is initial velocity. This has to be final velocity, 3.8 meters per second. Right? It started at rest, and after it traveled 6.8 meters per second down the incline, its velocity was 3.8. Well, that has to be final because it says after it traveled. What is the speed of the block when it is 3.4 meters from the top of the incline? So we want to know, and I didn't start at the top, but okay. If you want to back this up, fine. So we want to know what its speed, so we want to know what the final velocity is at 3.4 meters point. Okay, final velocity at 3.4 meters point. Now, how in the world do we get this? Well, let's look at what we have. We have, and now again, this is why it's so important to write everything down. Write everything down. It tells us it's constant acceleration. We have an initial velocity. We have a final velocity. We have a change in displacement. Don't worry about this yet, all right? Don't worry about that yet. We have constant acceleration. So what do we need? We have initial and final. We have total change in displacement. We need to know what the acceleration is. Well, I thought we had to find the final velocity. Well, you can't find the final velocity when it's halfway, because y'all, that's halfway. You can't find the final velocity if you don't know the acceleration. But I know what it is at 6.8 meters. I know what it is at 6.8 meters. So since it is accelerating at a constant rate, then I can use an equation and find the acceleration and then find the final velocity. Okay? So I need to find its acceleration first. Now, y'all, I'm just telling you, I know you think, right. Well, look, guys, most of your problems are not going to be one-step problems. I'm sorry, but they're just not. They're not going to be a one-step problem. I mean, that's just a general rule of thumb. That's physics, okay? That's life. Okay. You know, when I come to work, I don't do just one thing. I have multiple things to do. And sometimes it's things that I'm like, why does this have anything to do with what I'm supposed to really be doing? But guess what? I still have to do it. All right? And so most of these problems are not going to be one step. Some of them will, some of them won't. So, but I can find my acceleration. All right, remember I told you to memorize those kinematics, know those kinematics. If you look at how they're derived with calculus, with integration, you can use integration or the algebraic method. They'll help you to it'll help you to understand it. Well, you remember this one I said that we're going to use a lot? Now, how do I know to use that? Well, look, it says it's constant. This is a constant acceleration equation. There's my initial velocity. There's my final velocity. After it has traveled, its change in displacement is 6.8 meters. So I can find A. Now, I'm going to solve it for A. So A is going to be equal to what? A is going to be equal to, well, the initial velocity is 0, so that sucker's gone. So A is going to be equal to the final velocity squared divided by what? 2 delta x. Now, Ms. Shields, why did you solve it that way? Because that's really what you're supposed to do. And I know some of you are thinking like, well, no, duh, you're the teacher, you can say that. Well, I tell you what, because of the physics. Because now my physics is over with. The physics is over with. Now all it is simple mathematics. Okay? As Dr. Zatelli at Jacksonville would say, he said, you need to solve for the equation first and then plug everything in. Because that's the physics part of it, knowing how to write these equations so the physics makes sense and the math lines up with it. The math verifies the physics. So we take the final velocity squared, which was 3.8 meters per second squared, divided by 2 times, what was it for that velocity? Well, the change in displacement of the total displacement was 6.8 meters. And so we get an acceleration of 1.06 meters per second squared. Okay, now why is that important? Because now we want to backtrack and we want to know what the final velocity is at 3.4 meters per second. Okay? We want to know what it is at 3.4. Well, guys, you got to remember that the initial velocity is 0. So to find the final velocity, initial velocity 0 plus 2 times acceleration, 1.06 meters per second squared, times what? 3.4 meters. That's a 3. And you should get 2.68 meters per second, meters per second, 2.68 meters per second. Now look, I know that says VF squared. You got to go on and you got to take the square root of it. You got to do all that and then take the square root. I understand that. But I'm not going to do that step too. You ought to know how to do that step. The final answer, there you go. Take square root of both sides and you get the final velocity. Okay? I mean, I should not have to work every single step. Okay? Because again, y'all, that's the math part of it. You're already supposed to know that. Take square root of both sides and that's what you get. Okay? But I'm telling you that, okay? So you know that, hey, he's leaving out a step. No, I'm just jumping ahead. okay? And I told you what I did, so really I'm not leaving anything out. Okay? So, I'm assuming that y'all are math geniuses. Okay. Any other questions? Any questions about that problem? That one makes us think about what we're doing just a little bit. What about number 32? Number 32. Another good problem. Okay, we got a small rock that's thrown vertically upward. Okay. We're standing here. And we're going to throw a rock vertically upward. Okay. With a speed of 22 meters per second from the edge of the roof of a 30-meter tall building. Okay. All right, I got to back up. All right, so we threw the rock up right over the edge. And the building's height, and if you want to write it this way, height is 30 meters. Or you can say Y. Y is 30 meters. Okay, the height of the building, that is. And so we throw the rock vertically upward with a speed of, now what is that? Is that initial or final velocity? Well, what do we know about that rock when it reaches maximum height? What's its final velocity going to be? Anybody want to chime in?
Negative.
No, final velocity now. When that rock reaches its maximum height, what happens to, remember we talked about this a little while ago. When that rock reaches its maximum height, what's its final velocity? We know the acceleration is negative, yes.
Oh, zero.
They're very good, zero. So the initial velocity is what it's giving us, isn't it? And that's actually initial velocity in the y direction. Okay? And so that's 22, is it 22.0? I think it is. Yeah, 22.0 meters per second. Because the number of sig figs, it does matter, y'all. Even more so when you get into engineering school. You can't throw away numbers. Because remember, those numbers deal with the precision. Okay? And the building's 30 meters tall. The rock doesn't hit the building on the way back down and lands on the street below. So it's going to go up, and then it's going to go do all the way back down to the street. Boom. And it's going to wind up down here. So we're ignoring air resistance. Ignore air resistance. Okay. What it tells us. That's nice and sweet. What is the speed of the rock just before it hits the street? So we want to know what the speed of the rock is. That's actually its final speed. Yes, that would be in the y direction, in the y. Vy final. Just before it hits the street. Now that is A, so we're going to look at 32A here. Just before it hits the street. All right. So we know the height of the building. We know the initial velocity. What else do we know? I haven't written down everything we know. What's affecting that rock? What's causing that rock to fall?
Gravity.
Very good. And gravity, we're going to write it as negative 9.8 meters per second squared. Very good. All right. So we want to find the final velocity. Well, we can, can't we? Well, sure we can. Now, we need to go back and look at our data here just a little bit. Notice how I wrote the 30. Notice I told you height or y. Well, I'm actually going to use y here. All right? I'm actually going to use y. Notice where he's standing. Now, y'all, another thing about physics. Inertial reference frame. Where does everything start from? Are we where? In other words, if you were to put this on a coordinate system, a Cartesian coordinate, you drew the x and the y axis. Well, we're going to let this be x and that be y. Notice where he's starting. All right, he's starting right here at the origin. The rock goes up, but then, it gets down here, doesn't it? Well, what is that in the y? That's negative, isn't it? Now you say, why are you going over this? We got to keep everything in line. Because notice I wrote negative 9.8. Well, y'all, it really is. It really is negative 9.8 meters per second. Because the acceleration's always going downward. Even when you're going up, it's still going down. Well, how do you know? Well, if you're going up and your engine stops, guess what? You crash. Okay. So, we're going to have to label that negative, y'all, because it actually is. My initial inertial reference frame, where I began motion, I was at positive. When it gets below my feet, it's negative. I know I'm standing on the building, but still you got to understand that ball falls on down, or that rock falls on down, which is in the negative y direction. So we're going to say negative 30. So we're going to say y is equal to negative 30 meters. And see, it makes the math work beautifully. Now, there's a couple of different ways. We haven't really looked at the y kinematics yet, but we will. They're basically the same as the x constant acceleration. By the way, is this constant acceleration? It is it not? Gravity's constant, right? So this is a constant acceleration problem. All right, so you can actually take the kinematics that I showed you today in class in the x, swap out the x for y, and then make two other changes. Where you see plus a, make it negative g. Now listen, you don't say, well, okay, so when I plug in g, then it's negative times negative. No. The negative tells you that g is negative. You don't say negative times negative. Now, that's a common mistake I'll have students will do. Okay, when you look at those y kinematic equations, and I'm telling you they're exactly the same as the x for free fall, for the x, except you just, instead of x it's y, and then you make the acceleration negative and put g there instead of a. So let's look at it. So what equation can I use? One of my favorite, one that you use a lot. How can I find the final velocity right before it hits the ground? Well, y'all look, we know that when the rock gets back to the starting point, what's its velocity going to be? Well, it's going to be the same as it was when it left the hand, but in the opposite direction, right? Well, sure it is. So can we not use, there's a couple of different ones we can use here. The most convenient one to use is this one right here. V final squared, and of course that's in the y direction, is equal to V in the y direction initial squared. Now I can write it one of two ways. I can say negative. I can say negative 2g delta y, or I can say positive because acceleration is negative anyway. I'm just going to go ahead and do this. I can write it either way. It's still going to work out. If I write negative, well, let me just go ahead and do this. I'm going to say negative, I'm just going to say it this way, positive 2a change in y. And remember, a is g. Okay? So solve for the final velocity. Well, we know it's going to be what? The final velocity is going to be the square root of all of that right there, right? And by the way, that's v initial in the y squared plus, now watch, 2 times a what? A negative 9.8 meters per second squared times a negative 30. You can't take square root of a negative. It cancels itself out. All right? And so what do we get? we should get a final velocity of 32.7 meters per second. Now, is that the final answer? All right. Is that rock going up or is it going down? It's below my feet. Now see, y'all, now listen. This is where the conceptual stuff comes in. Okay? This is where the conceptual stuff comes in. The rock is down here at the street. Well, that's below my feet. That rock is not with reference to me. Because why are you referencing me? Because that's where the motion started. That's where everything began, with me throwing the rock straight up. So it's got to be negative 32.7. Now that, again, the conceptual thing comes in. It has to be because it's below my feet. It's down in the negative quadrant, negative y quadrant. Now, can I flip this thing around and keep everything positive? Well, I guess I could, but that would really be messing with the physics here. I mean, I could pull everything down here and da-da-da-da-da, but really that would mess all the physics up, because then I would be saying I'm starting at ground level when I'm not. I'm starting on top of a building. Okay, remember that negative sign tells me the direction. It tells me the direction it's headed. Okay. All right, I hope that makes sense. Now let's look at part B. I'm going to erase this. All right, so this is what? 32B? 32B. How much time elapses from when the rock is thrown until it hits the street? All right, so let's redraw it. Okay, we got the street. We're up here. The rock is thrown, then it comes up, then it goes, boom, it hits the street. So what is the time total, right? Total time, question mark. We'll know the time total. All right, do we have constant acceleration? Yes. Okay. And we know that constant acceleration is what? It's negative, isn't it? Okay. So how in the world do I find it? Well, look, y'all, we found the final velocity, didn't we? The final velocity was what? 32.7, negative 32.7, right? Meter, was it negative 32.7 meters per second? Yeah, meters per second. That's negative now. Okay, and the initial velocity was what? 22? Yeah, 22 meters per second. So we want to know time. We know g, which is acceleration, is negative 9.8 meters per second squared. Well, the math, just watch, the math's going to work beautifully. All right, do we have a constant acceleration kinematic that will help us solve this problem? What are we doing the x? Well, we're doing the y too. I told you a minute ago that just take the x and swap it for y and make the positive a negative g. That's all you got to do, okay, for free fall. Real simple. Just take the x kinematics, constant acceleration, swap the y for the x, and swap the a for negative g. All right. Okay. But I'm going to go ahead and write it the way we were talking, because I know we haven't covered that yet, so I'm going to go ahead and write it the way we covered it. But I just told you how to do it. So we're going to say v final. Which equation do I need, Mr. Shields? We'll find one that has final initial velocity and has acceleration and has time, because time is what I'm looking for. Well, it's this one right here. Real easy equation. V is equal to VI plus AT. Well, I thought you said use negative. Well, okay, I could. But just watch. Now solve for t. Well, hello, watch what's going to happen. We have V final minus V initial. I love it when the math all just falls into place. Divided by A, which is equal to T. Now the physics is done. We're done with physics. Now solve for T. Well, you're going to get a negative T. Oh, fool you. I'm not either. I'm not either. So plug it in. What was final? It was negative 32.7 meters per second minus, see how it just takes care of everything, 22 meters per second, divided by 9.8 negative meters per second squared. The negatives all cancel out, don't they? And what do we get? $5.58. Okay? 5.58. And you say, well, now, Mr. Shields, how can you do that? Because it went up and then it come back down. Well, all right, y'all. We're not taking the velocity, well, we are. We're taking it from the point here, but it is now negative because it's on its downward trek. Okay? Okay. 5.58 seconds. Okay? Any questions on that? All right, I think that's all of the even numbers. Yeah, I think it is. I don't think I skipped any. Okay. All right, does anyone have any questions? All right. I'm assuming no one has chimed in. I'm just going to pause for a minute.